Hello chemists, this is Ms. Placino and you're watching lesson 8.4 on half-life. In today's lesson we're going to talk about what role half-life plays in nuclear decay. Goals for today's lesson include defining what half-life is in relation to nuclear chemistry. We're going to be able to model radioactive decay. And finally we're going to perform calculations pertaining to the half-life of a radioisotope. This is the big one for today. Really important set of calculations for this unit. If you don't have a calculator handy, pause the video, grab one. It will definitely prove to be useful. Okay, so we've been studying nuclear decay, and when it comes to half-life, we're going to be focusing on natural transmutations, so things like alpha, beta, gamma, and positron decay. Half-life is just looking at the amount of time it takes for 1/2 of the atoms in a radioactive sample to decay. Again, the type of decay doesn't really matter. We're more concerned with how much time it takes for half of the sample to decay, hence the name half-life. Half-life is constant. There is nothing we can do to speed it up or slow it down. For that reason, sometimes we can use radioisotopes for things like dating. You might have heard of carbon dating, and carbon decays at a constant rate. So scientists can look at the amount of carbon-14 that is still present in a previously living organism, estimate how much would have been there in the first place, and then provide a rough estimate of how old that sample might be. We'll be talking more about uses of radioisotopes in a future lesson. Just like most of the other lessons in this unit, half-life is really going to lean heavily on the reference table. So table N is going to be incredibly helpful for half-life. Just to kind of remind you what table N looks like, we've got our list of nuclides, or just radioactive isotopes. We previously used decay mode. This was helpful when we were trying to write a balanced decay equation. Today we're going to be focusing in on half-life. If you look at half-lives, you'll see that the units are going to vary depending on what radioisotope you're looking at, so just be aware of that. Some half-lives are incredibly short. Calcium-37, for example, has a half-life of 175 milliseconds, so it decays extremely fast. On the other hand, something like cesium-137 has a much longer half-life, about 30.23 years. The length of half-life tells me a little bit about stability. Generally speaking, the longer the half-life is, the more stable the radioisotope is. So if we try to compare calcium-37 and cesium-137, because cesium's half-life is so much longer, it is safe to say that it is most likely more stable than the calcium-37 radioisotope. So let's delve into half-life in a little bit more detail. Let's say we're working with a sample of neon-19. Actually, it doesn't really matter what the sample is as far as how it's going to decay, but we're going to go through with an example of neon-19. So I can use table N. I can look up the length of a half-life. Go ahead and do that now. Yeah, it's a pretty short half-life. This is an unstable radioisotope. It's about 17.22 seconds. Just to review a little bit with decay equations, let's go ahead and write one. So we've got neon-19. 19 is the mass number. Use the periodic table. Find neon, it's element 10. Table N tells me that it undergoes a beta decay. I know that's my beta particle. If you've forgotten the symbol, use table O. So my resulting particle must have a mass of 19. It's going to have 10 on both sides, so it must have 9 protons. And if I use the periodic table, I would determine that I'm producing the fluorine-19 isotope. All right. So we're going to work with a, how many do I have there? 24 nucleus sample of neon-19. So to start, it's all radioactive. After one half-life, half of these atoms are going to decay. Just to make it easier to keep track of stuff, I'm going to kind of clump them together. But in reality, it's not like the top half is going to decay and the bottom half would still remain radioactive. They will be randomly distributed. But after one half-life, there we go. Half of them have decayed. So now these circles that are red, those are representing fluorine-19 nuclei. If a second half-life passes, we're going to lose half of the sample again. I've shown them in blue just to represent a second half-life. But again, now all of these red and bluish colored atoms are fluorine-19. What do you think happens after the third half-life? Yeah, we lose half of those atoms. They decay, they undergo this beta decay, and the sample keeps getting cut in half. You might be thinking, well, wait a second, if we had a fourth half-life, then we'd have 1.5 atoms left. Well, at that point, we can't have half of the atom decay and half of it not. So we'd either lose 2 or 1, and there's really no way to tell unless you just kind of conduct the experiment. So just to review, at the start, we ended up with 24 radioactive atoms at time 0, so no time has elapsed. After one half-life, we're down to half as many radioactive atoms. We've got 12, and one half-life must have elapsed. So that's 17.22 seconds. After the second half-life occurs, we'll lose half of the radioactive sample again to give us 6 atoms that are still radioactive. And 2 half-lives have elapsed, so that's a total of 34.44 seconds. 3 half-lives, we're down to just 3 radioactive atoms. Another half-life has passed, so that would be at time 51.66 seconds has elapsed, so on and so forth. So there's a lot of information I can take away from half-life. Okay. Here is a table of just kind of half-life and kind of dug some decay information. Whether you are working with a very stable radioisotope, a very unstable radioisotope, the identity, it doesn't matter if it's going alpha, beta, gamma, positron decay, half-life is going to look the same for every single sample out there. So after one half-life passes, we will have lost 50% of the sample, so 50% will remain radioactive. After 2 half-lives, we've lost another half, so 25% of the sample remains radioactive. 3 half-lives, 12.5. After 4 half-lives, 6.25% of the sample is still radioactive, so on and so forth. We can try to express that as a fraction remaining. That's remaining radioactive. So I can basically take these percentages and convert them into fractions. So half, a quarter, an eighth, a 16th, a 32nd. You can imagine more half-lives. We just keep increasing the size of the denominator. If I start with a 50-gram sample, after one half-life, well, I know half of it decays, so I'd be down to 25 grams. After a second half-life, I'd lose half of that, so I'd be down to 12.5 grams still radioactive. 6.25 grams after 3. And hopefully no surprises there. We're just constantly dividing by 2 to get to our mass. We won't be too concerned with sig figs at all with half-life calculations. Go ahead, try it out with 10-gram sample. After one half-life, 5, 2.5, 1.25 grams. And it's going to be kind of that same general idea for any sample. It does not matter, again, what radioisotope you're working with, how long the half-life is, or what type of decay it undergoes. This is going to be constant for all of them. We can also represent this graphically, or after 0 half-lives, of course, we have 100% of the sample remaining radioactive, and it just drops from there. Technically, sure, we may never get to the point where a sample fully decays, especially if it has a longer half-life, because you can keep taking a number and dividing by 2 again and again and again, and you know that you will never technically get to 0. Whether an atom actually decays or not is just based on simple statistics. Kind of like flipping a coin. You got a 50% chance of it being heads, a 50% chance of it being tails. The same applies with half-life. The atoms, of course, don't look around at each other and kind of figure out who's going to decay and who's not going to decay. They're not aware of the time. There's not some countdown going like 3, 2, 1, and then half the atoms spontaneously decay right on the spot. It's just kind of random statistics. So it's not going to be able to predict which atoms will decay. We can just say that, hey, over this span of time, we know that half of the atoms of this specific radioisotope will decay. Let's try out some practice problems with this and try to apply these concepts. So for half-life problems, there isn't really just like a specific formula that you're going to end up applying per se. It's kind of, you're going to have to figure some things out. So let's take a look at this practice problem. Question 1, the half-life of zinc-71 is 2.4 minutes. If one has 100 grams at the beginning, how many grams of the sample are still radioactive after 7.2 minutes? All right, so I've got the fact that it's zinc-71 doesn't matter. I know the half-life time, I know my starting mass, and I know how much time has elapsed. First thing I want to do is figure out how many half-lives occurred. So if I take time elapsed, and I divide by the time of a half-life, I should see that 3 half-lives have passed. The way I would do this, it's very inelegant mathematically, but I would take my 100 grams and I would divide it by 2 until I have 3 half-lives elapsing. So 100 divided by 2 would give me 50. Divided by 2, 25 grams. Divided by 2 is going to be 12.5 grams. And if I count my arrows, 1, 2, 3, those will represent my half-lives. So if I start with 100 gram samples at the beginning of some time period and 3 half-lives have elapsed, I should be left with 12.5 grams of zinc still radioactive. Let's try another type of problem. Let's look at question 2. The half-life of thorium-227 is 18.27 days. How many days are required for 3/4 of any given amount of thorium-237 to decay? All right, so if I have 3/4 of it decayed, that means I have 1/4 still radioactive. Okay, so I know I would start with 1. And if I divide that by 2, I'd end up with 1/2. If I divide that by 2, let's get rid of that, I would end up with 1/4. So that looks like 2 half-lives would have to elapse. So I can take 2 times my 18.72 days, and I can calculate how many days it would take for 3/4 to decay of my sample. Again, I'm not going to stress with sig figs here. That's it. Let's go ahead and let's take a look at question number 4. Give that one a shot. After 24 days, 2 milligrams of a 128 milligram sample remain. What is the half-life of the sample? The way I would attack this one, very mathematically inelegant, I would take my number and just keep dividing by 2. So I've got 128 divided by 2. It's going to give me 64. Divide that by 2, so that's 32. 2, so 16 divided by 2, 8, 4, and finally I've got my 2 milligrams. I'm going to count my arrows. 1, 2, 3, 4, 5, 6. So I know that 6 half-lives have passed. So if I have, sorry about that, 24 days, I think it tells us. And I've had 6 half-lives. 24 divided by 6 is, of course, 4. So it must be 4 days per half-life. Again, there isn't one specific mathematical equation to follow. When in doubt, basically start dividing by 2. That will eventually get you from hopefully some mass that you started with down to a mass that you've ended up with. Count how many half-lives have occurred, and you can use that information to either find like the length of a half-life, like we did in question 4, or you can use it to calculate how much time has elapsed, like we did back in question 2. Best way to get better with this, as with most concepts, is just to keep practicing with it. You got plenty of practice problems to keep you busy. Start chipping away at those. Don't forget to use the solutions online to check your work. All right, chemists, that wraps it up for today. Thank you for tuning in, and I hope you found this helpful.